So what is NMR spectroscopy? You've already done two forms of spectroscopy in spectrometry and mass, and IR spectroscopy. IR spectroscopy told you what about compounds? IR was specifically about the functional groups. NMR is beautiful because the reason why MR is beautiful is because of its power. That tool is extremely powerful. So the reason why NMR spectroscopy is so powerful is because it gives me almost a complete picture of the organic molecule. Like without having to do functional group tests using reactions or infrared spectroscopy, I can know not the functional group also, but even the alkyl groups, the size, the number of carbon atoms, everything. That's why NMR is so complete. It provides the most direct evidence for the whole structure of a carbon compound. Because unlike mass spec and IR, because we will do mass spec in molecules maybe in a bit after this chapter, a particular NMR spectrum will give the whole unique molecular structure of the molecule. Yes, it gets more complicated when you get like 20, 30 carbon atoms, but we won't be going there. You guys will be looking at the basics which are involving lesser carbon atoms. Now, what's NMR responsive? I mean, how do we do NMR? I mean, sorry, what am I saying this? NMR is basically how the apparatus is set up, and all of that has been removed from the syllabus. So if anybody is looking at questions and say, how does the NMR work? What is spin? What is nucleus? All of that stuff, nucleus spin is out of the syllabus. What's left is how we can interpret the graph to come up with an organic molecule. And uske liye there are two types of NMR spectroscopy we'll be doing. We'll be doing something called proton NMR and carbon-13 NMR. We will start with proton NMR and then do carbon-13. Proton NMR is much more detailed and also much more useful. And you can get most stuff by it. Generally, carbon-13 NMR only tells me the functional groups of the compound. Okay? For the first 2 days, we'll be looking at proton NMRs. Now, what is proton NMR? Now, I'll start with examples. Now, if you have questions in the middle, I would suggest wait, because most of the questions that you'll have will be coming up in the slide after that or the slide after that. So after some slides, I'll pause and ask you. Now, if something is bothering you, you ask, okay? So we'll go slide by slide and focus on if anything on the slide is something you don't understand. If it's the least of the questions, you hold on to them for a few minutes, I will answer them. So this is the end result first. This is what we're going to aim for. Okay, we should be able to look at a graph like this and come up with a structure like this. So what we'll do is we'll understand molecular structures and graphs together, so that when we get to see the graph later on, we'll be able to draw the structure. Now, what things which you see? What you will see are things called peaks. And I'm also talking about the stuff written in the next 2-3 slides because it's all together. I'm talking right now is on slides 5, 6, 7, 8, but it's my graph bada, so I've left it here. Now, first of all, in slide 5, you'll see I'm saying there are how many peaks? There are 3 peaks. And the 3 peaks correspond to 3 different, what we call chemical environments of the protons. The term proton will be used to refer to the nucleus of a hydrogen atom. But you can consider when I say proton that I'm talking about hydrogen. So, हम hydrogen की environment की बात करें, but technically I can't say that. I should say proton environment, but I'm really talking about hydrogen's environment. And what do I mean by hydrogen's chemical environment? The atoms it is bonded to around itself. Now, the 3 peaks are telling me that this hydrogen had 3 different environments. Even though the molecule, if you dekha jaye, so the molecule has 6 different hydrogens, but there are only 3 different environments. You can tell, at least by the color coding here, that these 3 that are labeled purple here are referring to this peak right here. Obviously, we'll talk about the x-axis values later. We'll talk about why the peak is higher and lower also. But this is a summary first, and then a detail. So, first of all, there are 3 different environments telling me that there are 3 different types of hydrogens in the environment. Aap dekha jaye, to you might see that these 3 are considered to be the same environment.
These two are considered to be one other environment, and this one is a third environment. Now, why are these three in different environments? We'll talk about that also. But ye तीनों हैं. And the heights or the areas of the three peaks, because area will be width into height, are in the ratio of the actual number of hydrogen atoms. इसमें एक है, इसमें दो हैं, इसमें तीन है. So the areas are ratio 1:2:3. Cambridge is so nice and most times writes the actual number of hydrogens for that peak on the top of the graph. So like you'll see things like this, 1, 2, and 3 also. Okay. Now, one thing on slide number 6 I'm mentioning is this, that let's skip to slide 6, that the hydrogens joined to the same carbon atom are considered to be the chemically equivalent. Hydrogen atoms, and I'll zoom in here for a second, look at this molecule. Look at these guys. The hydrogens, the three hydrogens on this carbon atom are considered to be chemically equivalent, meaning they have the same environment. And you can tell what I mean by environment. Look at this, the one on top. The one on top is bonded to a CH2, which is bonded to a CH2, which is bonded to a CHO. The one here is also bonded to a CH2, CH2, CHO. So that's why all these three have the same other sequence of atoms bonded to themselves. So these three are considered to be chemically equivalent or having the same environment. These two, by the fact that they are bonded to the same carbon atom, are also chemically equivalent. And so is this guy. So this is one, these two are equivalent, and these three are equivalent. That's another thing. So basically, if you're a hydrogen on a carbon atom, you're going to be chemically equivalent with the other hydrogens on the same carbon atom. Then we talked about next slide we'll see that the area I mentioned is proportional to the number of hydrogens in the environment. So this area is 1:2:3. Cambridge will give us the numbers in most cases 1, 2, and 3, but the area is actually 1:2:3. All right. So what do we know? That the number of peaks is equal to the number of different types of protons. Now, is a different term being used here, types of protons. Now, what makes a proton a different type from another one? When they have different chemical environments. Now, the term chemical environments, proton environments, or environment will mean the same thing in my class. Proton environment, chemical environment, all of three, this means that the atoms the hydrogen is bonded to. And if the environments are different for two different protons, then there are two different types of protons. Matlab, for example, if I scroll back up, and we had discussed this, that this is one environment, this is another environment, this is another environment. What I'm saying is these three are the same type of proton, but these two are a different type of proton. Aapas mein same hai, but these two are different from these. And this is the third different one. So is molecule mein kitne types of protons hain? 3, because there are 3 types of environments. So that term is now important. Type of proton means the environment of the hydrogens. All right. Now let's scroll down. So different types of protons ki baat aa gayi, theek hai? Then now this is very important. Our first job will be to figure out how if two protons are identical or in different environments. Okay. Generally, I mean, obviously we already discussed the fact that if the protons are on the same carbon atom, they are same. But we're going to have a lot more, we're going to have a lot more molecules that are going to be different. For example, if a compound has multiple CH3 groups and a CH2 groups, they will all, by default, they will all be different. Okay. So a CH3 will always be different from a CH2, it will all be different from a CH. But two CH3 groups can be the same or different. Look, let me say this again. Let's say you have a molecule CH3, CH2, CH3. I'm saying that the CH2 and the CH3 will be different aapas mein, because this has 3 hydrogens, this has 2 hydrogens. But if is this CH3 the same as this one, that will depend on a couple of things. So we'll talk about that. They might be the same or they might be different. What makes them same or different? We'll talk about that. So two CH3 groups may be identical in this case, By the way, in this case also they're identical. In this case they're also identical. But in this case they are not identical. And the reason is that it all depends on what the CH3 is bonded to. For example, in this case, the CH3 is directly bonded to an O. If this structure we've not done in chemistry before, but its bonding looks like this. So this structure that I've drawn right here is actually corresponding to this one. And why is this CH3 different from this CH3? Because the one on the left is directly bonded to O. The one on the right is bonded to a CH2. That makes these two different CH3s. But ye jo hai, why is this the same? Because this is the structure CH3 bonded to an O, which is also bonded to a CH3. Both of them are bonded to one oxygen. So they're both identical. Like you can draw and you'll realize it that symmetry kaam aayegi isme. Like if I make a line of symmetry right here, these two are identical. Isme main banata hu yahan, so it's not symmetrical. Even if I make the line here, those two sides are not symmetrical. When there's no symmetry, you know they're different. Symmetry means the same. Now I'll show you some examples first. Let's look at propanol, butanone, and then we'll talk about some more. We'll see a lot of molecules today, a lot of molecules. And that's the idea, to kill you with boredom. Huh? So this is the molecule, this is propanol, aldehyde with 3 carbons. This is the one we saw earlier. Now this one, these 3 hydrogens are to the same carbon, so they are equivalent. And these 2 are equivalent, and this is a separate one. And therefore we had how many different environments here? 3, and no identical environments, no identical groups. The next example on slide number 11, which I want to also correct, is that first of all is butanone, not nal. I don't know what I was thinking when I was naming this. This is butanone, a ketone. Now the ketone is, by default, this is a CH3 bonded to a CH2 bonded to a CO, which I will actually show, CO, CH3. And here you'll notice the 2 CH3s are not identical because this guy is bonded to a C double bond O, while the one on the left is bonded to a CH2. So these 3, so drawing them like this is easier to look because you can tell that these 3 must be the same, these 2 must be the same, and these 3 are on a carbon bonded to a CO, while these 3 are on a carbon bonded to a CH2. So these 3 are different from these 3, and the middle one is also different because it's a CH2. A CH2 will be different from a CH3. Okay? So here how many environments do I have? 3. And the amount in each environment has a number on top of it. Alright? So if we look at this and figure out how many environments are singing, I'm going to show you some more examples. Okay? Now here are 3 examples and I'll do them in detail in the next slide. Isme, this is CH3O, CH3 has 2 proton environments, one environment. That's why this is, and by the way, we're going to label them as HAs, each environment, or HB or HC. This is my way of labeling each type of environment. Kya ye alag hai, wo alag hai, wo alag hai. This is CH3, CH2, CH3, O, CH2, CH3. Let's look at these guys in detail. Let's start with the first one. This is CH3, O, CH3. These 2 CH3s are, because they're bonded to the same O, or you can say, okay, this CH3 is bonded to a OCH3 and this CH3 is also bonded to a OCH3. So they're both bonded to an OCH3. That means they're both equivalent. That means 6 hydrogens here have the same environment. So iska matlab agar kabhi graph dekhta main, if I were to see the graph of this, it'll only have 1 peak because the peaks will determine, the number of peaks will be because of number of different proton environments. Isme environment hi sirf ek hai. तो उसका ग्राफ जब कभी देखा जाएगा तो उसकी पीक सिर्फ 1 होगी और उसकी हाइट क्या होगी 6 because 6 हाइड्रोजन है उसमें. And look at the next example. This is chloroethane, CH3, CH2, Cl. And the H is, this is a CH2 and this is a CH3. By that it makes them different. For them to be identical, at least they have to have the same amount of hydrogens. Yeah, amount of hydrogens farak in CH3 and CH2. So these are 2 different proton environments. This is my way of labeling. Okay, this is labeled HA, then this guy will be a different hydrogen HB. But both of these are HV and all three of these are HAs. So I only have two types of protons. This is a way of labeling a hydrogen, HA, HB. You will see me use this a lot in the whole worksheet, in the whole notes. Then the third example is CH3O, CH2, CH3. We've seen this already earlier, so we kind of discussed this already. CH3 bonded to an O, this is a different proton environment. This CH3 is a different proton environment because this one is bonded to an O, this is bonded to a CH2. Now, our job for today is to look at each molecule and figure out how many different environments there are and how many hydrogens are in that environment. The ratio of the three peaks in this case would be, if you want to know, 3:2:3. So the areas of the peaks will be 3:2:3. So this CH3 and this CH3 ka height same hoga or area same hoga. So let's look at some examples right now. So let's look at slide 16 mein skill check question. So here I've got a molecule that is CH3, CHCl, CH2Cl. So sometimes it helps to write it in the condensed form, CH3, CHCl, and CH2Cl. So now look at this way, I clearly can tell there are how many different environments? 3. CH3 is 1, this is 1, and these two are 1. So 1, 2, and 3. So there are 3 environments, and of what ratio are they in? 1:2. Right now the ratio will be in the sequence, not of the graph, but of the molecule reading from left to right. That's all. This is for us internal use, for me to know, okay, are you getting the sequencing? No or no. So the ratio will just be from left to right of the molecule, okay? Now number 17. Now in 17, look at this molecule. Now this one, by the way, is called what? Butanol. This one is butanol. Its structure is CH3, then a CH, brackets OH, then a CH2, then a CH3. First of all, everything is without even looking at the environments, I know they're different because CH3 alag hoga CH se, OH alag hoga CH2 se. The only thing I'll check is, are the two CH3s identical? And to check, because one of them is bonded to a CHOH and one of them is bonded to a CH2. So I've got how many environments now? 1, 2, 3, 4, 5. You're missing out on the OH also, that's also hydrogen. So there's a CH3, the H on a C, the H on an O, the CH2 and a CH3. And the ratio would be 3, 1 is to 1 is to 2 is to 3. Absolutely. So now this is easy stuff. Generally they're all going to be all different like this. But what's also going to be needed is, if you're going to work out how many different environments there are, you must also consider if the molecule is symmetrical or not. Because I just showed you in the last 2-3 examples, they were not symmetrical. But hydrogen atoms on different atoms generally so if they're symmetrical, it's something else. We'll get similar environments. But if they're not symmetrical, then all of them hydrogen atoms on different atoms, like hydrogen atoms on a carbon and hydrogen on oxygen, they will be different. Let me show you by example what I mean. I think it's easier shown by examples. That's why don't worry about the words there. Ye molecule, dekho, this is pentan 3-one, guys. I'm sorry, it shifted. Yeah, this is pentan 3-one. Pentan 3-one is actually CH3, CH2, CO, CH2, CH3. I've made CH3, CH2, CO, CH2, CH3. Now, first of all, there are only 4 carbons that have hydrogens, not 5. This one has no hydrogen. Now, when I look at the molecule, it seems to me that if I make the line of symmetry here, the two sides are symmetrical. This side is CH3, CH2. This side is also CH3, CH2. What that means is this CH3, and this, by the way, symmetry is a shortcut to finding out. The real reason why this CH3 is same as this one is because the left CH3 is bonded to a CH2, CO, CH2, CH3. The right CH3 is also bonded to a sequence of CH2, CO, CH2, CH3. Looking at symmetry makes it faster to figure out, हाँ यार symmetric है, दोनों side same होंगी. तो इसका CH3 और इसका C बिल्कुल same होगा, और this CO2, CH2 will be the same as this CH2. So now we only have two environments. One is the purple one in this case, and one is the blue one. And the sequencing, the heights would be in the what ratio? 6:4, which will simplify to 3:2, but the heights will be 6 and 4. All right? So the 6 hydrogens are in the 2 equivalent CH3s. So by looking at even that, abhi humne condense banaya tha na, so looking at like this, it's easy to tell. So this is a faster way of looking at it. Once you get the hang of it, you'll realize that, you rather look at it like this, and you might realize that, wait, this CH3 and this is identical because symmetrical molecule tha, and we can label them HA, and then we can label this guy as HB, which is same as this. So I have only A's and B's, so I have 2 environments, and A's I have 6 of them, and B's I have 4 of them. Now somebody had asked me a question earlier, and I'll answer it. Okay, what would happen if you have CH3O, CH2O, CH3? Now without me answering, I will answer, but take a look at this. You can even figure out the answer to yourself. How many environments must this have? 2 environments, because there's a line of symmetry, which makes this CH3 and this CH3 identical. So they will be called HAs, and this would be your HB. So only 2 environments, and the height would be 6:2. So let's go to slide 21. Now in this case, this is a trick to use to also solve similar chemical environments. Sometimes it's not as, symmetry is one way, and another way is to use a trick. If you want to compare 2 hydrogen atoms, if they are identical, that means are 2 CH3s identical, or 2 CH2 are identical, what you should try to do is replace the hydrogen in the one that you're checking with Cls, and then examine the substitution product that results because of that. And once you have 2 different products, if the name is the same, then they're same identical. Let me explain what I mean. Let's say मेरे पास है butane. Clearly you can see a symmetry, right? So we already can tell इसमें कितनी environments होंगी. For looking at the symmetry example, symmetry explanation, divided in the middle, the 2 CH3s are the same and the 2 CH2s are the same. But let's say I couldn't figure out from symmetry. I'm saying the other. Let's say you want to compare these 2 CH2s if they are similar or not. A shortcut is, another way of doing it is that इन दोनों को compare करना ना आपको. एक example में इसका H replaced by Cl, and one example replaced this is H's by Cl. So do that, and you'll get 2 different molecules like this. Let's say CH2 की जगह Cl लगा दिया, then CH2, CH3. In the guy on the right, I'm going to replace the CH2 from the H from the CH2 on the right, because I'm actually comparing 2nd carbon and 3rd carbon. You see that? I've done that now. Then I try to name this fellow, and I name this fellow. What would I name this fellow? This is butane, but now we have chlorine, and chlorine is on what carbon? 2 if I count from the left. So this is 2-chloro-butane. Now name this fellow. You'll also count this, you count this from the right. And this is also called 2-chloro-butane. That's why they are chemically the same. Because by replacing them, you made the same molecule. So this hydrogen is identical to this one because replacing either of them makes the same molecule. So that's why symmetry works. The example on slide 22 also talks about the same thing. In this case, I have pentane. Now pentane is CH3, CH2, 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 CH3. And let's say I wanted to compare these 2. First of all, this and this. If I replace Cl here, it will become 2-chloro from here. If I replace Cl here, it will become 2-chloro from here. But might somebody say, well, why aren't these 2 the same? These 2 aren't the same, even though they're both CH2s, because if I replace the H here with the Cl, I'll actually get 2-chloropentane. But if I replace iska H with the Cl, I'll get 3-chloro. That means if their names change, that means they must be different hydrogens. That's why these two are not the same environment. They are different environments. That's one. These are ways of finding out. So in pentane, what you will realize is that you have, yes, if you look at this fellow right here, the ones on the left and the right CH3s are HAs. These are HAs. The middle ones are, these H's are HBs. And the center one is a different H, HC. And so I have 3 different environments. One of them has 6 protons, the other one has 4, and the middle one has 2. Then let's scroll down to some other examples. So here we see some more examples. This is 1,2-dichloroethane. Now the molecule is symmetrical. That tells me straight up कि ये दोनों same है. ये molecule symmetrical इसलिए नहीं है because of the Cl and a Br here. That makes it not the same. So this CH2 is different from this CH2, which is different from this CH2. Because it's not symmetrical. And all are bonded to different things. Only if I had done this, if I had said, acha nahi, CH2, 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 Cl. Now if I had done this, how many, this was symmetrical now, so how many environments would this have? These CH2 and this CH2 would be the same. And this would be a different one. So HAs and HB. Some more examples. This is an ester methyl ethanoate. Even though there are 3 carbons, there are only 2 environments because they're both CH3s, but they're different because symmetrical nahi hai. One is bonded to a CO and one is bonded to an O. The CO is a different H and the C double bond O, and the CH3 and O is a different H. So these will be 2 peaks, and heights kya honge inki or areas kya honge, because the number of hydrogens are there, 3 and 3. Remember, what we're doing right now is finding out the different number of environments and the protons in that environment. Why this is important? Because if we can do that, we can know what it means on the graph. Different environments mean a different peak for each environment, and the number of hydrogens will tell me the area of that peak. So iske graph, this ka graph will be only 2 peaks, and both will have the same height because both are ratios 3:3 or 1:1. This is ethanol. And don't forget the H on the O, because that also is a proton. So CH3, CH3OH. Because remember, this is about hydrogens, not carbons. Hydrogens. Yes, most of them will be on carbons. That's why it might seem like we're doing it for carbon. But it's for hydrogens on carbon, not carbon. Carbon ke alag se karenge. So इसमें a CH3 is different from a CH2, which is different from an OH. So 3 different protons. 3 peaks आएंगी. Heights will be in the ratio of 3:2:1. Now, let's look at a couple of more examples, and I'm going to get you guys to do a couple questions yourself. Here, we have propan-2-ol. Now, yes, the molecules look symmetrical, doesn't it? From the center. Yes? But sometimes people might draw this way for you. The same molecule can be drawn this way for you. And it might not be obvious to look at symmetry that way. And you might realize, नहीं यार ये तो symmetrical नहीं लग रहा. But इस तरह बनाया तो लग रहा, because इस तरह बनाया CH3COH, CH3H. Now symmetry is not the only way 2 hydrogen atoms are going to be equivalent. If hydrogen on carbons are bonded to the same carbon atom, what I mean to say is, these 3 hydrogens on a carbon atom, which makes it a CH3, are bonded to the middle carbon, which is also bonded to another CH3. So these 2 CH3s are the same group bonded to the same carbon atom, which makes these 2 identical in their environment. Even if they don't have symmetry, they will be identical in their environment. Even though there is symmetry hai, but symmetry nahi bhi hoti na, so these 2, the 2 CH3s on a carbon atom will give me the same environment. I'll show you some examples abhi. But right now, these 2 are identical, so their height will be 6, 1, and 1. So the ratio will be 6:1:1. A 4-carbon tertiary alcohol, 2-methyl propan-2-ol. This fellow is actually CH3, C, CH3, CH3. OH. It is symmetrical also, but what's beautiful is the H's on each CH3 are equivalent to the next CH3s because all of them are CH3s bonded to the same carbon atom, which is what makes them equivalent. The H's on the CH3 groups are attached to the same carbon atom and they will be equivalent. This is important. The hydrogens on the CH3 groups attached to the same carbon atom will be equivalent. So, ye तीनों CH3 groups will be equivalent, which means all these 9 hydrogens will be having the same environment. So, there will be 9 having one environment and 1 having a different one. Hence, the ratio will be 9:1. Because if I look at only symmetry, then I say, हाँ यार ये symmetrical है तो मैं सिर्फ इन दोनों को देखूंगा. Because if you only look at symmetry, then you forget the fact that even this is symmetrical to these two. Now let's look at a couple of questions. Obviously, this is easier when you look at the board because they're colored right here. But even if they're not colored, this would be, in the condensed form, would be CH3, then a CH with a Cl, then C with an H and 2 CH3s. That tells me that these two CH3s are the same. This is different from this CH3 because symmetry nahi hai. So this is different, that's 3, then 1. This is one environment, second environment, third and fourth. So how many different environments? 4. And the ratio would be 1:1:1:6 or 6:1. Whichever order, I don't care about the order, but you guys got the ratio right. Good. Now, skill check number 4. 3 environments, good. This is one environment, this is the other, this is the other. So 1:2:3. So now try the next two, 5 and 6, before I solve them. So in this particular case, I've got 3 here, 2 here, 2 here, and 1 here. So that's 4 environments in the ratio of 3:2:2:1. The molecule was not symmetrical, neither two identical CH3 groups. But going here, this is fun. This was a good question because what you must have realized is that there are 3 identical CH3 groups. So, therefore, the ratio is 9:2:1. And there were 3 environments because ye 3 ek environment the, these 2 are 1 and this OH is 1. Okay, 7. This one's pretty easy. 1, 2, 3, 4, 5. 1:3:1:2. It's definitely going to seem overkill, but the amount of molecules will do. But once the reason why doing so many molecules is that then interpreting the graph is easy because now you know what you're going to be looking for. You're not going to be looking for molecules, you're going to be looking for environments. So today is all molecule day. It's all molecules and their environments. Now let's look at this molecule. Now this here, and sometimes it becomes a little overwhelming to look at the whole structure, so I always write it in my own way that I like to. CH3CO, CH, and upar bhi CH3 hai, niche bhi. Now this makes it a little easier because I know I have 3 CH3s, but these 2 are identical. So I got 1, 2 environments and 3. And the ratios are 3:1:6. Beautiful. Absolutely. And then 9. There are 5 environments. 6:1:2:1. Because these 2 are CH3s. Right? Okay, now about the next one, 11. Guys, so let's do this together quickly. In dono mein, are they different or identical? Identical. So both are, I'll just use labels, HA, HA. So this is a height of 6, that's it, right? In these, the next one, what do you get? It's symmetrical, so these 2 are the same, and 6:4, because these guys will be H. Yeah? What about this one? This is symmetrical, but the 2 CH3s are the same, and this one is H let's 6:2. इसमें कितनी environments हैं? 3 environments, because this CH3 is different from the last CH3, and the middle one is, let's say, HB. क्यों different है? Because that's a CH3 bonded to a CO, and that's a CH3 bonded to a CH2. Symmetrical नहीं है. So the height will be 3:2:3. Yeah? Then I do 13 for homework. I want to do 15. Last one. Now this is nice. I'll give you a moment to think about this and then I'll solve this. This one has actually only 2 environments, and the reason for that is, guys, because this is combining the symmetry part and the part that the 2 alkyl groups are on the same carbon atom. First of all, it's symmetrical hai. That means whatever these two are these two same, but these two are also identical because they're both on the same carbon atom. So if these two are HA, this is HA, then this must be HA. But if these two are HA and the symmetry, so these must be also HA. So these all are HAs, HA, 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 and HA. And then the other two are also symmetrical, so they must be HBs. So I got 2 HBs and 12 HAs. So 12:2. And it's okay, but now you can look for these things also, right? So tomorrow we'll start chemical shear, which is the y-axis values on the graph.